Torricelli's theorem. We can use Bernoulli's principle to find the speed of a fluid coming out of the spigot of an open tank. The result is called Torricelli's theorem. Since both points 1 and 2 are exposed to air, they have the same pressure, atmospheric pressure, P0. We will also make the assumption that the speed of the liquid surface lowering at point 1 is so slow that it can be set to 0. So as the water flows out of this spigot here, this surface level here is decreasing, but so slowly that the velocity is 0. Since the pressures at both points are equal and V1 is 0, let's go ahead and simplify Bernoulli's equation. All right, these will cancel out. This will go to 0, and therefore we have rho g y1, so that's this height here, equal to rho g y2, and that's the height down here, plus 1/2 v2 squared, and that's going to give us that kinetic energy of the water flowing out. There's a rho in each term here, so we can cancel those out. Solve this for v2, because we're trying to figure out how fast is that water coming out of this spigot, and we get this equation right here. Wait, doesn't that look familiar? The velocity with which the liquid leaves the container horizontally at point 2 is exactly the same velocity that an object would have if it were dropped from a height of delta y. Isn't that amazing? So in kinematics, if you drop an object a certain height, this is the same equation to figure out how fast it would be going at the bottom point. Open the PhET simulation, Fluid Pressure and Flow, the Water Tower tab. Water tower problems are a great way to review projectile motion. So the third tab is the Water Tower tab. We can just open that up, and look, the water is sinking. It's all flowing out. It's projectile motion. We can match leakage so that it won't run out of water. We can increase the height. We can see the speed. We can use a ruler to figure out how high up it is. How far away is the water going to land? What's the pressure at the top versus down here? So very cool simulation.